Okay, good morning, guys. So it's time to start our class. Um, just before starting the class, just a couple of announcements which I want to make, and I'm not going to repeat it again and again. So please take a note of that. So the first thing is, as you can see, I have added one more file, which is some messages for you. And this is for all the sections. So please take a note of that. Uh, the first thing is I took the attendance manually in the first class, but from now onwards, I'm not going to take the attendance manually. I'm going to take the attendance electronically from the Zoom meeting room. Okay. So the Zoom meeting room will record when the student logs in and when the student logs off. So from there, I'm going to take the attendance. So please log in on time. And the second thing is I can call your name anytime during our class for any discussion or for any questions. So you should be there to answer it. Okay. And you can look at the other ones. Only this one I want to emphasize, please, as I have done it in the last class also, in your Zoom profile, please, you log in with your proper name, that is your first name and your last name. And please include your KFUPM email ID, that is the which starts from S2000 something something at kfupm.edu.sa. Please include that email ID. Please include that in your Zoom profile. And also keep your webcam on. Keep your webcam with you. I can ask anytime to turn on the webcam during the class discussions or during the quizzes. Okay, and the webcam should be of a good quality. The remaining things you can go through these instructions. Okay, but please, I'm telling you once again, your first name, last name should be properly available when you log in. And the second thing is your email address should be registered with your Zoom profile. Why I'm telling this is whenever I generate the attendance or even the class interactions, which is the poll report, I should it will list the the names of the participants and their email addresses electronically. It will list all of them. So it will be easier for me to identify. Again, I'm telling you, please do that. For example, again today I can see a couple of students who hasn't say logged in with proper name. So please don't do that. Okay, so let's start our lab.
Doctor,
Yes.
is it possible to move to Microsoft Teams?
Microsoft Teams will be difficult for me. That's why I have started. I tried Microsoft Team in the last semester, but I did not I did not feel comfortable with that. So that's why I'm using Zoom. Okay.
Okay, Doctor.
Okay. So let's start. So in the last class, just to give a review, quick review, in the last class, we spent time on quickly reviewing the coordinate system and how to get the surface surface areas, infinitesimal surface areas, and for all the three types of coordinate systems. To start with our chapter 4, just remember that these coordinate systems will again be reviewed by the instructors of the lab, because this week is the no lab week, but next 2 weeks you have problem session 1 and problem session 2 and 3, where they will review the coordinate system. They will you are going to visualize the different planes of the different coordinate system. You are going to use the surface integrals. You are going to use the volume integrals, and also you are going to use the divergence theorem, Stokes theorem, and also the curl, all these things. So this will be a review to you, as we are going to use all of them in our course. Okay. So now let's start. Uh, so electrostatics. So electrostatics, our first part is the Coulomb's law. So as you can see, the Coulomb's law. I'm sure you have already looked at Coulomb's law, probably in your physics 102. Here we are just trying to represent the Coulomb's law using vectors. So it's not just the scalars, but it's vectors. So what does the Coulomb's law stating? So the Coulomb's law is stating that if you have a charge, which is Q1, and another charge, which is Q2, and they are at two positions. The positions are defined by the position vectors. So as you can see, they are defined by the position vectors. This is the position vector R1, small r1, and with an arrow. So remember, in our course, Sadiku book, it uses either arrow or it uses sometimes, if I'm not mistaken, capital letters to represent a vector, or it uses the italicized alphabet or italicized term to represent the magnitude. Okay. So in our case, I'm making it much simpler. So anything with an arrow is a vector. So this charge, its position with respect to origin, so this is your origin, is R1 bar. And this charge Q2, whose position vector with respect to the origin is R2 bar. So these are the charges Q1 and Q2. Then according to the Coulomb's law, which is an experimental law, it has been found experimentally, it says that the F12 bar, that is the force on 2 due to 1, that is the force on the charge Q2, that is the force that this charge will exert because of the presence of this charge Q1, is given by Q1 Q2 over 4 pi epsilon R12 square, R12 square times A, this is small a, R12 bar. Now, what is this small a, R12 bar? Small a, R12 bar is a unit vector. So it's a unit vector. See here, it's small a, R12 bar is a unit vector. And what is this R12? R12 is the distance vector. So these are the position vector. This is the distance vector. That is, it is the distance vector which is pointing from the charge Q1 to the charge Q2. So this is its direction. So this is the distance vector from here to here. This is the distance vector. And its direction is from Q1 to Q2. And this unit vector A, R12 is nothing but it's the unit vector which is pointing in the direction of the distance vector. So the unit vector AR12 bar is the unit vector which is pointing along the direction of the R12, the capital R12 vector, which is the distance vector. Okay, so this is the Coulomb's law. Now, this unit vector you can easily find, that is AR12 bar, a unit vector along the direction of R12 is nothing but the distance vector R12 bar divided by, see guys, here I'm not putting an arrow here on the top. So if I'm not putting an arrow here, it means that it's the magnitude. Okay, it is the magnitude. So what I'm doing, it's the distance vector divided by its magnitude will give me the unit vector along the direction of the distance vector. So definition, this is comma. So the distance R12 is nothing but it is the distance vector pointing from Q1 to Q2. And similarly, if you see here, it is R12 square. That is the magnitude square. This is the magnitude square. Now, if we go further, what is this epsilon? Epsilon is called as the permittivity of the material. So where these two charges are placed. So is that in free space? Is that in vacuum? Or you are looking that inside any material? So that epsilon is called as the permittivity of the material. So what is this permittivity of the material? It's a unique property of a material. So every material has its unique properties. So these unique properties are captured under permittivity. So we name it as permittivity. And it's not just one, this property, which is permittivity. There are other one also. We call it as permeability, and we also call it that conductivity. So all these things, all these terms, they completely define any material. Okay, and one of them is the permittivity. We will go and we will talk about this permittivity, permeability a little bit in brief, because we will not go into too much detail, but we will talk about this in brief in our subsequent classes. Okay, so as of now, we know that it is a permittivity, and if my charges are in free space, okay, free space, then the permittivity value epsilon can be replaced by epsilon 0, because this epsilon 0 is the subscript 0 represents that it is the permittivity of the free space. Okay, epsilon 0 represents the permittivity of the free space. And again, it's a constant, it's a measured quantity which has been done experimentally long time ago, and its value is 10 to the power of minus 9 over 36 pi, or 8.85 times 10 to the power of minus 12 farad per meter. I'm sorry, this m should be small because meter is small m. Okay, so this is F12 was the force. F12 was the force. See, let us see how this F12 is seen, is looking like. It is like this. So this is F12 force. So if you have this charge Q1, if you have this charge Q2, then the force exerted on Q1 due to Q2 is in this direction, which is the unit vector AR12 direction, or I can say it is along the direction of your distance vector. Now, in a similar way, you can also find the force that Q1 is experiencing because of Q2. So it will also exert some force. Now, what is that force? That force, we named it as F21. That is the force on charge 1 due to charge 2. And if you see here, is equal to minus F12 bar. So if you see it is its magnitude, this force magnitude is same as this force magnitude, but it is in the opposite direction. That is, it is in the opposite direction. That means it is along minus AR12 unit vector, because AR12 unit vector direction is this. So it is in the opposite. So that's why it is minus AR12, or I would say it is in the opposite direction of the distance vector. Okay. So now what I am doing is I am now simplifying this force expression. So if you see here, the force, this was the force expression. So now I'm simplifying it. So what I'm doing is this unit vector, I'm replacing it with this one, which is here. And therefore I'm getting the force as Q1, Q2 over 4 pi epsilon. Now this is R12 cube, and this is the distance vector R1. Now what I'm doing is I'm now representing this distance vector by this position vectors. So the position vectors are known to us. That is, the positions of our charges are known to us. So how can I represent this distance vector in terms of position vectors? We know that the position vector R1 plus the distance vector R12 must be equal to the position vector R2. So therefore, your distance vector R12 is nothing but your position vector R2 minus your position vector R. Now, if I substitute R12 distance vector in terms of position vectors in this expression, then I will get as Q1, Q2, R2 bar minus R1 bar over 4 pi epsilon, because R12 represents the magnitude. So that's why there is a mod here. So it is R2 bar minus R1 bar, and then it's cube to the power of 3. So that's why it is to the power of 3. So this is the force in terms of charges and in terms of position vectors of the charges. And this, let's look at, we know it very well, that if Q1 and Q2, they are of the same sign, we know it very well. If Q1 and Q2, if they are of the same sign, which is the case here, what we have derived, all these, see, they are of same sign because I'm assuming them to be plus and plus. So plus and plus. So that's why I'm not writing here. Or if it is minus and minus, so it is minus into minus, it becomes plus. So it will be the same thing. So what will happen? They will repel. So that's why this force F12 is trying to push your charge Q2 away. And similarly, the force F21 is also trying to push your charge Q1 away. So that is, they are repelling. So the Q1 is going in this direction, Q2 is going in this direction. That's why they are repelling. But if they are of opposite sign, if they are opposite sign, any one is positive or any one is negative, then what will happen? Then we know that
They will attract.
yeah, the force on Q2 due to Q1 will no longer be this one. It will be in this direction. So this will be your F12. Similarly, the force on Q1 due to Q2 will no longer be here. It will be in this direction. So this will be the F21 bar, and this one be F12 bar. And this is because 1Q will be negative. So the overall, your force will have a sign of negative. Okay. And this is what I have summarized in that 2 points, which I have written here. See, these ones. So they are of same sign. Then F12 will be parallel to the unit vector AR12. F21 will be parallel to minus unit vector AR12, which I have already told. So they are repelling each other. But if Q1 and Q2 have opposite sign, then F12 will be parallel to minus AR12. So it will be coming towards Q2, will be coming towards Q1. And F21 will be parallel to AR12 because Q1 will be coming towards Q2 and AR12 is the unit vector which is going from Q1 to Q2. So this is what I have summarized here. Okay, so now let's go to the next page. So here I am showing some examples. So if you see here, we need to find the force. So we have two charges. The second charge Q2 is -1 nano. Nano is 10 to the power of -9 Coulomb. And this is placed at this particular point in space, which is 1, 1, 0. And you have another charge Q1, which is 3 nano Coulomb. And it is placed at this point, -2, 3, 0 in space. And we need to find the force on this charge, Q2, because of Q1. That means we need to find F12. We need to find F12. So how do you do it?
Using the formula, doctor,
Yeah.
that is above.
Yes, exactly. So first, so if you see here, here you have Q2 and here you have Q1. So we need to find F12. To find F12, so first what we are doing, we are first finding the unit vectors. The position vectors. We know the point. We know the point. So position vector R1 is nothing but it is AX plus AY plus 0 AC. This is called the position vector R2. And position vector R1 is -2AX plus 3AY and 0 AC. And I hope you remember how to find the position vectors. So the points, from the points, you just write the vector and that becomes the position vector. And now the distance vector is R2 minus R1. So subtract them. So AX minus of -2AX will give me 3AX and AY minus 3AY will give me -2AY and this is gone. So this is my position vector. And now if I find the force, so it is Q1, Q2, R12 bar over R12 bar over 4 pi epsilon naught. So see here, I'm now replacing it with epsilon 0. So epsilon, I'm replacing it with epsilon 0. Why? Because in the question, it is free space. So that's why I'm allowed to replace epsilon with epsilon 0. And this is equal to, so substitute all the charges. See, I'm now substituting in coulombs, not nano coulombs. So I'm replacing it, replacing nano with 10 power minus 9, 10 power minus 9. This is the distance vector. And this is the magnitude of the distance vector. And this is the epsilon 0, 4. And what we are getting is minus 1.7 times 10 power minus 9 AX plus 1.15 times 10 power minus 9 AY. And the force is in newtons. And if you want to see its representation, it's like this. Okay, because it is easy to visualize. The reason is Z is 0. So that's why it's just an XY plane, right? So XY plane. So you are just looking in the XY plane. So therefore, your P1 or your Q1 is here -230. So the -2, this is 30, and Q2 is 110. And how is the force? The force is attractive because one is positive and one is negative, and this is the direction of the force, that is towards them. And this is the distance vector, which always points from Q1 to Q2. Okay, so now we have seen the force. So we have looked at the Coulomb's law, and from there we found how we can get the force which is exerting on charges. Now here what we are doing is we are now defining another term, which is the electric field intensity. Now what is this electric field intensity, which is defined as E bar? The symbol is E bar, and it is defined as force on the charge divided by the charge. That is the force per charge. That is called as electric field intensity. So E bar is nothing but F bar over Q, and its unit is in volts per meter. Volts per meter. So it is newtons per coulomb, but newtons per coulomb, if you go and if you look at it, eventually you can represent newtons per coulomb as volts per meter. So volts per meter is the most commonly used unit. Force over the charge. And it is very, very similar what we have seen here. See what I'm doing here? I'm again considering two charges. Now, this is my charge Q1, and there is, instead of Q2, I'm putting a test charge here, small q, test charge. Okay, let's assume that it's a test charge. Excuse me. And this is the point P where we are finding the electric field intensity. Okay, we are finding the electric field intensity. So now, since this is small q, so I can just represent this as a distance vector. I don't need to say 1, 2. So this R bar, we know that it is the distance vector pointing from my charge Q1 to my point of interest, which is P, where I have placed a test charge. And this is the distance vector the position vector R1, and this is the position vector R. So now I'm simplifying my force subscripts. So that's why I'm not using 1, 2. I'm not using 1, 2 because our objective is to find the force here. That's it. So therefore, the force F, which is exerted on this test charge, which is placed here, because of an existing charge in free space, Q1, which is placed here, is given by small q, Q1 over 4 pi epsilon, R bar over RQ. Okay. Now, what I am doing is, from this force, I'm finding the electric field intensity. So I know this is the force here, right? This is the force here. Now, can I find the electric field intensity here at this point P? Yes. So therefore, the electric field intensity E at the point P, which I'm naming it as my observation point, and where I have kept my test charge Q, due to the existing charge Q1 is given by E bar is the force at that point divided by the charge at that point. So the force is F bar. Charge, what is the test charge at that point P, is small q. So therefore it is F bar over Q, and F bar we have already got here, substitute here. So small q cancels. And then if you see here, you will get the electric field intensity as Q1 times r minus r1 bar in terms of position vectors divided by 4 pi epsilon r minus r1 bar. So these are the position vectors. So this is called the electric field intensity. So hence the above equation gives the electric field intensity E bar at the position point P due to the existing charge Q1. So I kept this, guys, I kept this test charge just for, you can think that just for mathematical purpose. Okay, I have just kept that test charge for mathematical purpose, but eventually this will be gone. As we have seen, it's already gone. So this is the electric field intensity, which you will observe here due to a charge which is in the free space. In our case, it is Q1, which is placed here. Yes, Taha.
Doctor, what if I wanted to find the intensity at Q1 position?
If you want to find the intensity at Q1 position, so let me just complete it, and then I will answer the question. So this is called as the electric field intensity. Now remember one thing: electric field intensity is always caused by the existence of a charge in the free space. So it is something like this. Think about the following. In a room, you have placed one charge, which is Q1, this one, Q1. You have placed it somewhere, okay, any position. Now that charge Q1, will create an electric field intensity in the whole room. It will create the existing electric field intensity in the whole room. So now what will happen if you try to bring, okay. So now what will happen is if you try to bring any test charge from outside and put it in this room, then that test charge will feel a push, either a push or a pull. Okay, push when that test charge is same as they are of the same signs, or a pull when they are of different times. So this kind of a field which is created by this charge Q1 around itself, okay, is nothing but your electric field intensity due to that charge Q1. Got it? Due to that charge Q1. So again, I'm saying just visualize it. If you put anything in the room, because a charge Q1 is already there, so it has created its own electric field intensity around itself. Now, if you try to bring any charge and keep it anywhere in the room, that charge will experience a sort of push. Okay, it will exert some sort of push. So that is nothing but the electric field or the electric field intensity. So try to visualize from that point of view. So that is called as electric field intensity. Now to answer your friend's question, you can get the electric field intensity here. But if you want to get the electric field intensity here, you need to have your charge Q1 placed somewhere, right? Because again, I'm saying this small q was, think that it's a we just placed it for our mathematical purpose. We placed it for our mathematical purpose. So in this space, we had only one charge. And to find the electric field intensity of that charge for our mathematical purpose, we placed a test charge and then we found it at this point. And eventually this charge was cancelled. So I hope I have answered, Taha.
Yes.
Okay. So this is how it is created. Now, if you want to visualize how would be the field, how would be the field uh, of this charge. See here, how would be the electric field of this charge if my charge is placed here. And remember, whenever I am referring to charge in our lecture, I'm referring to a point charge. It's like a point charge. It's very, very small. You can think that it is the charge which is available at the tip of a needle. So that is called as point charge. Then if this is the point charge, then how would be the electric field intensity? Electric field intensity will be everywhere. See, it will be everywhere. This is what I was trying to show you. Okay, so we will come back to that a little bit later. Now, let us take an example. So calculate the electric field intensity. We need to find the electric field intensity at this point. Okay, this is let's assume that this is our point of interest, which is -1, 1, 0, due to a charge Q1, which is -5 nanocoulombs. And this charge Q1 is located at 1, 0, 0 in our free space. So it's a free space. So again, you can you can relate this example that you are placing a charge Q1 of -5 nanocoulomb at 1, 0, 0 in a room. Okay, so we can assume this room in a rectangular coordinates, and then we are trying to keep it at 1, 0, 0. And then because of this charge Q1, whenever you place a charge Q1, as I told you, it will exert an electric field around it. Okay, we cannot see, but when we try to bring a charge, then the charge will experience a pull or a push, and that is your field. And we want to find what is that field at -1, 1, 0. What will be the magnitude of that field at -1, 1, 0? Or I would say, because as you can see, it depends on the distance vector cube and how far is the charge. So the electric field will change its magnitude as you go far away from the charge. This, you know it very well, right? You remember this. See, the distance vector. So it's the magnitude of the distance vector cube. So if this R increases, if this R becomes large, then your force or your electric field value will go down. It will decrease. So, okay. So here again, your electric field is Q times R bar minus R1 bar. So what is your R bar? R bar is your distance vector, is your position vector of your point where you want to see the electric field intensity. So that's why it is minus AX plus AY minus, and R1 is your position vector of your charge Q1, which is 1, 0, 0. So that's why it is just AX. So this is my distance vector divided by 4 pi epsilon, this mod R minus R1 Q. So if you simplify this, it is 8.05 AX minus 4.05 AY volts per meter. Now let's visualize this. What is happening? So see here, again, it is easier for us to visualize because your Z is 0. So you are in the XY plane. So your Q1 is placed at 1, 0. So this is 1 and Y 0. So here is my Q1. and my point is -110. So it is -110. So this is my point and this is Q1. And how is the electric field? See the electric field. Can we find the direction of the electric field? See here, how is the direction of your electric field? Positive AX. So that means this is the positive AX and negative AY. So if this is the direction of AY, because these are the unit vector which is pointing along the XY. So this is AY, then negative AY will be like this. So if this is my negative AY, then my resultant will be, this will be my result, which is my electric field intensity. So what I'm trying to tell you here is the electric field intensity is pointing towards the charge. See, the electric field intensity is pointing towards the charge because this charge is negative. Because this charge is negative. So a negative charge will have all the electric field direction towards it. All the electric field direction towards it. Whereas the positive charge, it will have the electric field direction always away from it. You can check this. It can have away from it, or you can look at this example. So this is positive. So the electric field will point away from it because it will point in the direction of your R position vector. So it is away. So if you see here, this is the summary. So here, this is my charge positive plus Q, and this is my charge minus Q. So if I have a charge of plus Q, if I placed in a space, because that's why it is greater than 0, and suppose if I place at origin, then its electric field will be radial. So now think from the spherical coordinates point of view. So from the spherical coordinates point of view, you are placing this charge at the origin, and if you select this as your observation point, the electric field will be in this direction. If you select an observation point like this, the electric field will be in this direction. If you select your observation point like this, the electric field will be in this direction. So the electric field will be radial. So radial, in a way, it will be pointing in every direction. It is ready. It has already exerted this kind of sort of pressure everywhere around the charge. The charge has created this kind of pressure everywhere, and it is radial. It is radial. It is going away. So if you place anything, if you place any light charge in this, if you place any light charge in this, suppose I place it here, then it will feel a push away from it because the electric field intensity is going away. So it will feel a push in this direction. And when I'm talking about radial, you think it in this manner. It's a 3D representation. How should I show it in 3D representation? See, if this is the center, then it is not just 2D. Everywhere it is. So you can think it as a spherical shell. So what is a spherical shell? Spherical shell means it's like your football. Okay, football. That is, it's a hollow from inside and it only has a surface. So if I place this at the center, if my charge, then all these arrows, assume that all these arrows are hitting that ball surface. Got it? They are all hitting that ball surface. So therefore, it is everywhere. The field is everywhere. And that's why I'm trying to represent it this with a dashed one. This is not a circle. Try to visualize it in the 3D. So it's a surface of your ball. It's a surface of your ball. Inside it is hollow. And at the center origin, we kept a charge Q. So your electric field intensity will be going out from everywhere on the surface of your ball. So that is your visualization. It is going away. If the charge is negative, then it is coming towards it. Correct? If the charge is negative, then it is coming towards it. So this is the charge, which electric field, which is created by a point charge. If it is positive, so these are the notes which I have just now explained it to you. So the notes are, see, the electric field lines, they are radial with respect to x. So they are, they are radial, and the lines enter for q is less than 0 and leave for q is greater than 0. That means for a positive charge, the lines goes away from the charge, and when the charge is negative, the point, the arrows will come toward the charge. Then electric field lines, they are always perpendicular to the spherical surfaces centered at Q. So if this is the spherical surface, which is nothing but your ball, then if you try to see the electric field lines, they will all go out from these spherical surfaces if you have a positive charge. And when they go out, they are always 90 degrees to that spherical surface. Okay. And if you want to find the magnitude of your electric field at this point or this point or this point or this point on the spherical surface, wherever you go on the spherical surface and you select any point on it, your electric field intensity will be the same. Okay. So this is the point charge. Now, till now we are talking about a single point charge, right? Now you can have many point charges in a room or many point charges in free space. Example, see here. I have one point charge, 2, 3, like this. I have n point charges in this free space. Now, can I find its electric field intensity at this point? Yes. We found the electric field intensity of, okay guys, so it's time now. Maybe we will continue this in our next class. Okay. Anything you want to ask before leaving?
Doctor,
Mm-hmm.
for the profile name, it's first name plus the last name, and you mentioned something about the KFUPM ID. We put it
you can,
next to our name.
Yeah, when you create your profile, it will ask you your first name and your last name and also your email address. So try to keep your KFUPM email address there.
Complete KFUPM, like the ID, then at kfupm.edu.sa.
Yes.
Oh, okay.
Okay.
Okay, fine.
Okay. Anything else?
Yeah, Doctor, did you take attendance?
Attendance, as I told you, I'm going to take it from electronically from Zoom. Okay. Okay then.
Okay.
Thank you very much, guys. Anything else? Okay.